Hey everyone, welcome back, and today let's solve Leetcode problem 802 titled Find Eventual Safe States. So there is a directed graph of n nodes with each node labeled from 0 to n minus 1. And the graph is represented by a zero-indexed 2D integer array graph, where graph at index I is an integer array of nodes that are all adjacent to node I, meaning that there is an edge from node I to each and every single node in graph at index I. And a node is a terminal node if there are no outgoing edges. And a node is simply a safe node if every possible path starting from that node actually leads to a terminal node, or effectively another safe node. And we need to return an array containing all of these safe nodes of the graph, and we have to have them sorted in ascending order. So a lot of different constraints, a lot of different kind of factors to think about in this problem. Let's best understand what it really means in example 1. So in this case, our graph is actually, as expected, a 2D integer array. We have 1, 2, 2, 3, 5, 0, 5, and 2 empty lists, right? So effectively, our output is going to be 2, 4, 5, and 6. Why do we have an output 2, 4, 5, and 6? Well, because these are all of these safe nodes of the input graph of the problem, right? And notice how all of these node values are actually sorted in ascending order. But why are these the only nodes in the input graph that are actually safe? Well, the reason why is because every single possible path that starts from each and every single one of these nodes, every single possible path leads to a terminal node. And to reiterate what a terminal node here, in this case, a terminal node is simply just a node if there are no outgoing edges. That's what makes a node a terminal node, if there are no outgoing edges from that node, right? So as you can see, the reason why, the formal explanation of why 2, 4, 5, 6 is the output. The given graph is 1, 2, 2, 1, 2, 2, 3, 5, 0, 5, and 2 empty lists. And in this case, nodes 5 and 6 would be terminal. Why is that? Well, let's just kind of graphically analyze this. There are no outgoing edges from either one of these nodes. As you can see for 5, we have some incoming nodes or incoming edges that are going into this 5, kind of the arrows pointing to this 5, but we don't have any arrows that are pointing away from this 5 and starting from the 5, meaning we don't have any outgoing edges from this node 5, and the same logic can be applied to this 6. Neither does it have any incoming edges for that problem as well. So 5 and 6 are the two terminal nodes. We want to find all of these safe nodes that every single path that starts from that node leads to a terminal node, so either 5 or either a 6. In this case, the reason why 0, 1, 2, 3, and 4 are not terminal nodes is because each and every single one of those nodes do have, or rather, do have outgoing edges, right? In this case, 0, as we can see here, does indeed have an outgoing edge, right? It goes from 0 to 1. And also from 0 to 2, and from 0 to 3 as well. And 1 also has an outgoing edge going from 1 to 2 and 1 to 3, so does 2, and so on and so forth. 3 also does as well, and so does 4 going in to 5. All of these nodes, 0 to 4, are actually non-terminal nodes because they do have outgoing edges. 5 and 6 are the only nodes that are terminal, and so we simply return 2, 4, 5, 6 because they are the safe nodes that have every single path starting from them lead to either a 5 or a 6, one of the terminal nodes that we have in the input. Every path that starts at 2, 4, 5, and 6 all lead to one of these two terminal nodes. In example 2, we see that the graph is 1, 2, 3, 4, 1, 2, 3, 4, and 0, 4, an empty list. And in this case, we only have one safe node. That's going to be this 4 right here. Because, of course, only 4 is actually a terminal node as our node, and every single path that starts at 4 also leads to 4. And so in this case, 4 is actually both a terminal and a safe node. So for the constraints here, we see that n is going to be the length of the input graph, and that's going to be within 10 to the 4th power. And we also see that graph at any index size length is always going to be less than or equal to n, and graph at ij is always going to be less than or equal to n minus 1. Note that graph is actually a 2D integer array input. We're also given that graph at any index I is always going to be sorted in strictly increasing or simply just ascending order, and it also may contain self loops, which we will get into a little bit later in this problem. And the number of edges in the graph are always going to be in the range from 1 to 4 times 10 to the fourth power. So with the problem statement, constraints, and examples out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so what are some observations or key kind of takeaways that we can really get from this problem statement and so on and so forth to really help us lead to our most efficient solution? Well, kind of to simplify what a safe node really is, to better understand what the problem is really asking, effectively in layman terms, a node is basically considered to be a safe node if every single path that starts from that node eventually not only leads to a terminal node, but also no cycles are involved. And what do I really mean by no cycles? Why do we really have to check for cycles for nodes to see if they're safe or not? Well, again, a node is safe if all the paths that start from that node eventually lead to a terminal node, right? A terminal node, again, is one that doesn't have any outgoing edges. However, the reason why cycles are important is because if any node is part of a cycle, we know that it cannot be safe. Why? Because paths that start from it would get trapped in that cycle forever, never ever exiting that loop or cycle and going to any terminal nodes, right? So for example, to better picture this and kind of get a visual demonstration of this, if we have node 0, and this per se goes to node 1, and that node 1 per se goes to node 2, sorry, let me capitalize that, and then let's say node 2 actually goes back, kind of wraps around, to node 0. Well, this would literally be a demonstration of a cycle. Because let's think about it. Node 0 goes to node 1, great. Node 1 goes to node 2, great, nice and linear. But then node 2 comes and goes back to node 0. Why is this really a cycle? Well, think about it. If we get to node 0, we're eventually going to lead to node 2. If we get to node 2, we're eventually going to lead to node 0. And this cycle or pattern is going to continue forever. We're going to go to node 0 to 1 to 2 to 0 to 1 to 2 to 0 to 1 to 2, and so on and so forth, continuing that pattern forever. It is a cycle. We cannot exit that cycle and hence never actually reach a terminal node. Right? That is the very important part here. In this case, node 0, node 1, and node 2 are all part of the cycle. Any path that starts from these nodes would never ever reach a terminal node, a terminal node. And so we can automatically say that these nodes right here, node 0, 1, and 2, they are not safe. And so we basically have to eliminate all of the nodes that are part of or even lead to cycles. And once we've actually removed all the cycles from the graph, the remaining nodes would either be terminal nodes or they would lead to terminal nodes, and that would make them completely safe. Okay, well, now that we've actually understood what cycles are, let's go ahead and talk about the high-level rundown of our solution. Effectively, the way it's going to work to actually solve this problem efficiently, we're going to be using graph traversal. Pretty simple, straightforward method, simply just traversing through the graph as you may have thought of. Basically, the first thing that we're going to do is actually reverse our input graph. And the reason why is because one observation that we can really make to help us lead to our solution is that really instead of tracking where all of the nodes lead, it's actually much easier to reverse the edges and track which nodes lead to any given node. And that way, very efficiently, we can actually start from terminal nodes, again, nodes with no outgoing edges, and actually work our way backwards. And we can also use topological sorting with a variation of the Khan's algorithm, right? Let me actually spell it out here. Khan, it's basically a Khan's algorithm variation. Right? And the way this is going to work, basically we're going to use this variation for topological sorting to actually process the nodes in the reversed graph to actually help us eliminate all the cycles to get all these safe nodes in our input. But you may be wondering, okay, what exactly is topological sorting when we actually kind of talk about it with Khan's algorithm? For a quick high-level rundown of how topological sorting really works and how it actually helps us identify all these safe nodes in our input, basically, topological sorting is meant for graphs, and it's basically a way of actually arranging the nodes of a directed acyclical graph, also known as a DAG or a DAG, in a linear order, such that for every single directed edge from U that goes to V, node U would always come before node V in that specific ordering. It's basically like saying before we actually do task V, we have to complete task U because task U or node U goes or leads to node V. Right? And the reason why it really helps in the context of this problem, the reason why we're actually using a variation of topological sorting to actually get these safe nodes is because, first of all, we can start with the terminal nodes and then gradually process the nodes whose outgoing edges already lead to previously processed nodes. And that always ensures that we always process the nodes in a safe order and always eliminate cycles. And the reason why this approach is very effective is that a graph with cycles cannot have a valid topological order. And effectively, by repeatedly removing nodes with 0 indegrees, and what indegrees are, basically they're nodes that don't depend on any other nodes, we're basically just breaking the graph down into smaller components, into kind of subproblems, if you will, right? And effectively, if any cycle exists, they will be left out of this process, and that will actually help us identify these safe nodes a lot more efficiently. And kind of like a quick reference of what that really means, think of like a group of tasks where some tasks depend on others. If we actually arrange the tasks in an order where every single prerequisite is handled before starting the next task, well, think about it, that is a topological sort. If we have to do task A before we can get to task B, simply place A before B, or node A before B, and that would be an example of topological sorting. And in this case, all the safe nodes are like tasks that can eventually be completed without any dependencies getting stuck in cycles, right? That is kind of the reference that you should be able to have to solve this problem using topological sorting with the Kahn's algorithm variation. And let me actually comment this out before it actually bugs your code. Node 0 goes to node 1 goes to node 2. We already talked about that, so let's not worry about that. Okay, well now let's get back to the high-level rundown of our solution. Effectively, like I said before, we're going to be using topological sorting with Kahn's algorithm to actually help us eliminate cycles. So for the data structures that we're going to be using an adjacency list to actually store the reversed graph for all of our nodes, and an in-degree array to actually count the incoming edges for every single node. And finally, we're going to be using a queue to actually process the nodes with 0 in-degree. Right, and effectively by the end of our program, the nodes left in the queue would actually be our safe nodes as such, and they would actually have to be sorted in ascending order, which is something that we can kind of handle at the end of our program. So now let's actually get into the main code here. So what I usually like to do for graph and matrix problems in general is actually grab the length of our graph and just store it in n, because that's also what they call it in this problem as well. So we'll get the integer n to be the length of our input graph. Very straightforward graph, again, keep in mind, is actually a 2D integer array, and we're simply going to actually use this to actually store the number of nodes in the graph and help us iterate through all the nodes efficiently later on. Okay, well now that we've actually got the length of our input graph, now let's actually get that reversed graph and actually start reversing the nodes. So I'm literally just going to call it the reversed graph, and it's going to be initialized to a default dictionary. In this case, our key type or key data type is going to be in form of a list. And effectively, once I've actually initialized that, let's actually initialize our in-degree array. In-degree array, and this is going to be all zeros with dimensions of n, basically an array of size n, where n is the length or number of nodes in our graph, and 0 are going to be the default value for every single cell while actually initializing it. And to reiterate, reversed graphs, the default dictionary, it's going to be a default dictionary of lists to actually store the reversed edges, and a list of size n would be our in-degree, right, to actually store the count of incoming edges for every single node. And keep in mind, all of the lists as such, or all the indices, are all initialized to 0 once we actually initialize this in-degree array. So now let's actually kind of reverse the graph and populate or update our reverse graph and in-degree for all those specific nodes in that for loop here. So for every single source or source node in the range of n, keep in mind where n is the number of inputs we have in the graph. Sorry about that, guys. Let me zoom back in. For every single source in the range of n, and for every single destination, so I'm literally just going to say for every single dest in short form for my iterator, in the graph at that specific index source, keep in mind we're going to basically have it in form of 2D integers, so 1, 2, 2, 3, for every single destination in the specific node source in the input graph, we're going to update our reverse graph and in-degree for that specific node source and destination. So what I'm going to first do is actually update my reverse graph. So I'm going to say reverse graph at that specific destination and append to that specific key the source. And similarly here, with kind of similar logic, I'm going to update the in degree at that specific source and increment its specific value by 1, right? Effectively, we're iterating through every single source node in the input, right, n times, because n is the number of nodes we actually have in the input. And effectively, we're going through every single node and simultaneously its outgoing neighbor's destination, right? And first of all, in the reverse graph, we're adding the source as a neighbor of the destination, and at the same time, for every single iteration, in our in degree, we're incrementing the in degree of source because it actually does have an outgoing edge. We're incrementing the number of outgoing edges that it actually has. Okay, well, now that we've actually stored every single source with its destination nodes, and also you could say descendants, and we've actually got the number of outgoing edges for every single source node in the input, now let's actually initialize our queue. I've always struggled with the spelling of queue. I believe it's spelled like this with 2 U's and 2 E's, and it's going to be initialized to a double-ended queue. And the way I'm going to initialize it is actually use something called list comprehension in Python. It's simply going to be a list for every single node in the range of n. So it's going to be a node for every single node in the range of n, iterating through n times, if the in degree of that specific node, if it's actually equal to 0, because that tells us the number of outgoing edges. Because keep in mind, in degree, the actual array that we initialize, simply stores the number of outgoing edges for every single source node in the input. And we only want our queue to be initially initialized with all of the nodes that have an in degree of 0. That means they have exactly 0 outgoing edges, and that also means that they're terminal nodes. Because keep in mind, terminal nodes are literally defined to be a node that has exactly no or 0 outgoing edges. That's exactly how the problem statement actually defines such nodes, right? Effectively, once we actually initialize the queue with all of those things, we're, again, using list comprehension to find all those nodes and actually use them for processing in the future iterations of our cons algorithm variation here. Okay, well, now that we've actually initialized our queue, let's actually get the safe nodes kind of result here. Our return answer, it's going to be initialized to an empty list, and as you may imagine, it's going to store the eventual safe nodes, and we're simply going to append it for every single safe node that we find as we actually iterate through the input. Okay, well, now let's actually process the queue and all the nodes in it, starting from the terminal node. And usually the way we do that in graph problems is typically say while the queue is non-empty, which really just means that while the queue still has nodes to process, we want to actually process the nodes and continue our graph algorithm, right? So while we actually do have nodes to process in the queue, we're first going to pop a node from the front of the queue, right? So the way we can do that is actually initialize node, and it's simply going to be it's simply going to be queue dot pop left. We're literally, as you may look by the method here, we're popping left from the queue of the frontmost value or node of the queue, right? Once we actually pop off that frontmost or leftmost value in the, node in the queue, we'll actually append that to these safe nodes, right? Because we know it's guaranteed to be safe. And so we can simply just say safe nodes dot append in Python as our keyword, the actual current node. Right, we're literally popping the node from the front of the queue and adding it to the safe nodes because we know that it all automatically is guaranteed to be safe, and we can add it to our return list of all the safe nodes we actually have. Okay, great. Once we've actually added this specific safe node to the node, now let's actually iterate through its descendants, or in other words, its destination nodes. So for every single neighbor, if you will, I'll call that as my iterator for it to be more readable and understandable for the code. In the reverse graph of this current node here, simply iterating through all the different descendants or neighbors of the current node in the reverse graph input, while if the current in degree, so if the in degree, I should say, sorry, and keep in mind the in degree is the number of outgoing edges for the current node, if the in degree and the current neighbor, if it's equal, or rather, my bad, mess it up. I should first actually decrement its value by 1. So in degree at neighbor should actually be subtracted by 1. Sorry guys, messed up my order here. Now, once we actually subtract its value by 1 for its specific outgoing edge, well, now we can actually check if it's equal to 0 after subtracting it by 1. So if the in degree, at this specific neighbor if it's now equal to 0 after subtracting 1 from its outgoing edges, well then we know we can also append to our queue for future processing the current neighbor. Right? And the way this really works is effectively we're iterating through again all of the neighbors in the reverse graph of the current node and basically decrementing their in degree. And if any neighbor node's in degree becomes 0, we know we can add it to the queue for future processing. And effectively, once this while loop is actually done executing, we simply have to return the sorted of our safe nodes because the problem specifically states that we want to sort our safe nodes in ascending order. Right? We're literally doing this because the problem constraint actually wants us to do so. So unless I made any syntax errors here, this should be accepted and this would be a valid solution. And as you can see, this really is just about as efficient as you can get it to be. So for a quick high-level rundown of how our code actually works, effectively first we're reversing the graph to actually make it easier to trace the nodes that lead to terminal states, and we're using topological sorting by processing the nodes first with 0 in degree, marking them as safe, and moving on to future nodes, and ensuring that all the cycles are eliminated, leaving only the safe nodes that we add to our safe nodes return result. So I will give you guys a few seconds to kind of just think of this problem yourself and actually actually try to solve the runtime and memory space complexities by yourself. And then I'll tell you guys what the complexity of this problem and solution really is. So I'll give you guys a few seconds to kind of just think through that, and I'll be back in like 20 seconds. Okay, so getting back to the memory and space complexity, the time or runtime complexity for this solution is actually going to be a big O of V plus E total, or fully, right? V is going to be the number of nodes in the input, and E is actually going to be the number of edges. The reason why we actually have this runtime complexity is because to actually build our reversed graph, as we see on line 6, that's going to be a big O of E complexity, right? The number of edges. And to actually process all of the nodes as a bottleneck, that's going to be big O of V plus E, right? In the while loop and actually in this initial loop as well. And so the fully bottleneck or fully simplified complexity is going to be big O of V plus E for the reverse graph and also for the in degree array, right? And basically for the memory or space complexity, it's also going to be big O of V plus E because again, we're actually using auxiliary memory, these extra data structures. We have this in degree array here, and we also have this reverse graph actually using extra memory that scales proportionally with our input. And so our, our memory complexity is actually going to be big O, or rather is actually going to be big O of V plus E. Okay, well, I actually wanted to kind of get back to our decrementing by 1 for the neighbor node in each iteration of this topological sorting. Why do we actually decrement the in degree value when actually solving problems in general with topological sorting? Again, in degree is the number of outcoming or rather incoming edges in a node, right? And effectively, what we're really doing is actually processing a node. Once we actually process it, we're removing that node and its outgoing edge from the graph. For example, if a node U had an outgoing edge to node V, if we removed U, that would mean that V now has one less incoming edge. That would be why we actually decrement the in degree of V whenever we actually process the node U. Okay? And effectively, basically to actually identify nodes with no incoming edges, basically again, nodes with an in degree of 0 are independent. They don't depend on any other nodes, basically like our input terminal nodes. And by actually decrementing the in degree of neighboring nodes, we're basically discovering the new nodes that now have an in degree of 0 that are potentially safe. And these nodes are actually safe to process because they no longer have any more dependencies. Right, we're breaking these cycles, we're identifying the nodes with no incoming edges, and we're actually simulating the dependency resolution, right? Because decreasing the in degree would mean resolving dependencies, because when a node's in degree actually reaches 0, that means all of its prerequisites have actually been processed, and that means it's actually ready to be added to the list of the safe nodes, right? For a quick kind of analogy, again, Imagine you're actually organizing a project where some tasks depend on others. Task B would depend on task A, and task C depends on task B. Once task A would be complete, we know that it no longer counts as a prerequisite, and so we can decrement the number of tasks that task B depends on. And finally, when task B has no remaining prerequisites, that means its integrity becomes 0, and it's ready to actually be worked on next. So to kind of fully reiterate, we're decrementing the integrity to actually simulate removing a node and its outgoing edges and discovering the nodes that no longer have any dependencies, which again really just mean its integrity is 0, and efficiently just resolving dependencies using that topological sorting method. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye bye.